Right, so this is the Pearson Edexcel Further Maths AS paper, Core Pure paper number 1 from 2018. If you're doing the whole regular A-level, then it's still good practice, I think, to do these. If you're just doing the AS paper, then of course yours will look very similar to this. It's 80 marks and you get 1 hour and 40 minutes. Let's get straight into it. Now this is a matrix, it's only 2 marks to invert this, which is a giveaway that all you have to do is put this straight into the calculator and you'll get your answer. So that's 2 free marks just for knowing how to do that. If it was worth like 6 marks, that means you have to do it by hand, but just look at the marks for how many it's worth. And of course, if there's algebra in here, you can't do a calculator either. But anyway, solve the simultaneous equation this. Now we notice, of course, that these coefficients are made up of this matrix here. So we can write that out like this. So it's this matrix times x, y, z into these 3 numbers here. And of course, if we front multiply both sides by this inverse matrix, so put this inverse matrix here, that will all multiply to make just the identity and just go away. And then front multiply this one here to make this, and now we can just solve this for x, y, z. Again, you can just shove this in a calculator, and you get your 4th mark just by knowing how a calculator works. And then interpret this, well, these are 3 planes, this is a plane, this is a plane, this is a plane. This is the meeting point of the 3 planes, so all planes meet at a single point. Which is this one here, and we get 5 marks very quickly. Good, so this has roots alpha, beta, gamma. Tell me the cubic equation that has roots this, this, and this. All we have to do is make the substitution w equals 2x plus 1, rearrange that for x, and then just shove that into here. I should have said z's every time, really. Okay, let's just say that this should have been a z, this should have been a z, and then put that z value into here on each one. It's not going to make a difference to the answer. I also don't even think I would have lost any marks for that, but it's possible I would. Make that a z, make that a z, and then just shove it in. And yeah, I think I times everything here by 8. So that times by 8, that times by 8, this times by 8 is 24. And the reason I did that is because that just makes all of this fraction go away. Because 2 cubed is 8, so that just all goes away. And I mean, it's just simplifying and collecting here to do, and eventually you get your answer, which is good. Yeah, I should have probably put some z's here because that's what this is written in. It was because the one I did this morning was written in x's, so I just copy pasted it. That was a different paper. Anyway, this here, we need to rewrite this for them because it needs to be z minus a single thing. So put that in brackets and say it's 1 plus I with a minus here. And now this represents a circle, center 1, 1, radius 3. So that's fine. And this here is 2 lines starting, or 2 half lines I should say, starting at the point 2, one with angle of pi over 4 from the positive x-axis and one with 3 pi over 4. Now I've said here gradient 1 and minus 1. Now the reason I know that, if we just draw it very quickly, so here's the circle by the way, center 1, 1, radius 3. Now pi over 2 is straight upwards, 0 is acrosswards, so pi over 4 must be right in the middle, which means gradient 1, and likewise pi is over here, pi over 2 is up here, so 3 pi over 4 is halfway between those and is straight across like this, gradient minus 1. So that's how I knew those straight away. You've got a starting point at 2, so we put down 2 here, and say the pi over 2 line gradient 1 goes this way, and 3 pi over 4, sorry, now that's gradient minus 1 as I said. If this starts at 2 and this is the point 1, 1, then 1 across 1 up takes you to here, so this line goes straight through that center. And we need to be between these 2 lines and we need to be within the circle, so we're going to shade this region in here for our answer. And now we're saying that this complex number w satisfies the fact that we're on the circle, it's not just inside it, but on the circle, and we're on this line. So we're clearly this point here. The easiest way to find out what the point is just to pretend you're not doing complex numbers anymore and just make everything in Cartesian form. So, for example, this circle in Cartesian is x minus 1 squared plus y minus 1 squared equals 3 squared. Remember to square the radius. And this line in Cartesian, again, the gradient is 1, as I've said. So it's y equals x. And then if you just go down 1, and across 1, and so on, you just get to minus 2. So that just must be that. And yeah, we can just shove this into here to get this, expand everything out, collect everything together, and we end up with this, which has solution that, if you put it in the calculator. Of course, now putting this into that, the 2's actually cancel, which is nice, we get y is this. And so our complex number is, this is the real point, because remember x represents the real axis, so this is the real bit, and this is the imaginary bit, so this is the complex number here, with the real bit here, imaginary bit there. And we're looking for that, the modulus squared of that, which just means we need to square each of these things and add them up. So we need to square this, add them up. Of course, this expands out, so you get 4 first, and then you have the cross term, so this times this is actually root 14, but you got 2 of those, of course, you got the other one as well, and then plus this thing squared, which is just 14 over 4, I believe, and this thing squared again is just 14 over 4. This is 7 over 2, and 7 over 2 make 14 over 2, which is 7, plus 4 is 11, and we'll have our answer. And we don't need to square root because it's looking for that thing squared anyway. Question number 4 is a vectors question, it looks like. So we've got water pipes which are being modelled by a line, or straight lines, and we've got a road which is modelled by a plane, and that's the equation of the plane. Line passes through these 2 points. Now I may as well just work out the vector of the equation of the line because that's always helpful. So just pick one of the points. I always pick the first one I see, and then the plus lambda, and then this direction vector is what you need to get from here to here. So I need to add 2 in the x bits, I need to add 3 in the y bits, and the z bits don't change, so that's 2, 3, 0, and that's the vector equation of this line w. Now I've written this here because this, and it's not in the formula book unless I've just missed it, but this is the formula to work out the angle, the acute angle, between a plane and a line, where n is the normal of the plane, and the normal of the plane can be written because of these 3 numbers. So this is just x, y, z dot these 3 numbers, and this is the normal to the plane. So this is a different way of writing this thing here, but this is the normal, so that's the thing I'm going to use for n. And then b is just the direction of the line, so this vector here. So okay, b dot n is this dot this, which I can work out is -9. The modulus just means I can use a +9 later on. The modulus of b is 2 squared plus 3 squared plus 0 squared, which is nice and easy. Modulus of n, a little more tricky, but you've got a calculator. And then the angle is going to be sine theta equals 9, because I can just modulus that, over root 13 root 358. Do sine inverse, and you get this answer here. A point -1, -2, 0 lies on the road, so that's on the plane. So I can't be bothered to draw the plane, but you've got this point on some plane somewhere, and then you've got the water pipe somewhere else, and you want to get from the plane to the line or from this point on the plane to the line in as short a length as possible. So okay, we need how do we do this? Well, obviously that line is going to meet the line connecting the point to this line is going to meet at 90 degrees to be as short as possible. So that's very useful. What you can say is okay, let's just call that point x where they do meet. We've got an origin somewhere. And what I can do is I can represent the vector c to x. So this is the point c, this is the point x. C to x, I can go, instead of just going c to x, because I don't know how to do that, I can go from c to o and then from o to x. And c to o is just this vector swapped, because the whole point of this vector is it describes how to get from o to here. So swap that over for 1, 2, 0 to get backwards. And then o to x is just this. That's kind of the point of this description here, is to get to any point on the line w, you just go to this point, which is on w, and then you add lambda amount of this direction until you arrive at the point you want to get to. So, okay, to get from c to x, we can do minus this vector plus all of this, which we can all put together like this. The 1's cancel plus 2 lambda, and that makes 1 plus 3 lambda, and that makes -3 plus 0 lambda, and that's c to x. Now the useful thing about that is that c to x dotted with the direction of w is 0 because they meet at 90 degrees. All right, so this dot that must be 0. And now I can solve for lambda, because this makes 4 lambda plus 3 plus 9 lambda, and you have to trust yourself here because this does not give you a nice lambda. So it's really tempting to think that you've messed up somewhere, but this is correct. You just need to trust yourself and keep going. Plug that lambda into this line w to find the coordinates of this point. You can use a calculator, so it's not too horrific. And then we need to find the distance from c to w, from c to this point x, which is on w. And of course, to do that, you need to first find the change in dx, change in y, change in z, which is, well, this is -13 over 3, isn't it? So the distance here is 6 over 13. And the distance here, this is 26 over 13, so the distance here is 4 over 13, and the distance here is clearly 3. Square all those, root them, and you'll put it in a calculator, and you'll get this. Now, all of these distances are in meters, and they want the answer in centimeters, so this is 305 centimeters, I think, to the nearest one. Good. Question number 5. Now, I don't remember anything about matrices, but thankfully the formula book gives you this. You can see that I've Control F'd matrix to find this. So okay, I recognize of course that all of these are exact values, so if I could just find the theta that perfectly gives me all of these, that's just the rotation anti-clockwise about O. So okay, I think with a bit of trial and error I can find that quite easily. 2 pi over 3 will do it. That'll get me exactly this perfectly. So therefore, for 3 marks, all I have to say is this is an anti-clockwise rotation of angle 2 pi over 3 about O. That's all I need to say, I think, and I'm done. The transformation V, represented by this, is a reflection on there. Now again, it's only 1 mark. Most of you have probably been trained to know what that is, but you can just use this. It's in the formula book, right? So reflection line y equals -x means I need tan theta to be a -1. So I can just solve that. That's minus pi over 4. You could, of course, use the positive value if you wanted to, but just shove minus pi over 4 into there to give you this, and type all of those values in, and you get this vector matrix here, which is good. So we can use the formula book nice and easily there. Given that u is followed by v, so we just need to be careful to get these transformations in the right order. We're doing u first, then v. Now u is this one, which is this in numbers. So we take a coordinate xy, we apply this matrix first, which means we put it here next to it, and then we apply v, which is this matrix here. So it's not reading left to right. Like if you're just lazy and go left to right, you put this one left, then this one, then this one. But it has to be this one first acting, then that one. Now, of course, we can just multiply these two matrices together to find the singular matrix that would do it. 0 times this plus this, and this is this, and then that's still 0, and then this gets you this, and so on, and you get this matrix here. And then show that there's a real number such that 1k is invariant. Invariant means that that point doesn't move. So when you apply this matrix to 1k, you still get 1k out. So okay, let's just multiply this out. So this times this is just this, and then plus a half k is 1. Just reading from top, so this times this plus this times this is 1. And then this times this, which is half, plus this times this is k. And we just need to hope that we get a consistent answer here. So if we double all of this and add root 3, we get this, so that's nice and easy. And if we double all of this and then take away root 3k and factorize, we get this, and then divide and we get this. And now these two things aren't initially the same when you look at them, but of course we can rationalize this. 1 times this is just itself. That makes a 4, cross terms cancel, minus 3, which is just 1, and we have the same thing as we did before. So if k is 2 plus root 3, we have an invariant point there. Good. Number 6, so we've got a very standard thing to do here. We take this, we expand this bracket out, so it's 3r minus 2 times 3r minus 2, which is 9r squared, minus 6r twice, isn't it? So minus 12r plus 4. And of course we can use these standard results again just from the formula book here. We break all of this down into 9 lots of the sum of r squared, minus 12 lots of the sum of r, plus 4 lots of the sum of 1. You're expected to know that the sum of r is n into n plus 1 over 2. And the sum of 1 is just n, and this one you can just use this formula for. And yeah, at this point I just look straight at the answer and think they want me to take a half n out. So I can do that. I can take a half n out of this. This actually makes 9 over 6, which is 3 over 2. So if I take a half n out of that, I remove the n obviously, 3 over 2, take a half of that, and it just becomes a 3. Leave the other things alone. Take a half out of this, obviously you just remove the fraction and take that n out as well. You're just left with this stuff. And then 8 times a half n gives us, it does give us 4n, so this is all fine. This, if I just check over it, gives me a quadratic, so I'm quite happy just to expand that out, because I know I could just tidy it up if I need to, and I end up getting the answer, which is good. So cool, so that definitely works. Hence this thing here. This is quite an interesting question, and I think quite a hard one. Firstly, just read very carefully. Look at this 5 here. Just read it very carefully. Look, there's a 5 here, so that's not quite the result we've just got. So we first need to say this thing, right? The sum from 5 to n is the same as the sum from 1 to n minus the sum from 1 to 4. You can work this out, right? Just by saying, well, when r is 1, you get 3 minus 2 is 1 squared. When r is 2, you get 6 minus 4 is 6 minus 2 is 4 squared, and then 7 squared, and then 10 squared. This thing is the result we just found, and this you can just tidy up to make this. So that's this thing, and now we can maybe consider, and just type that into a calculator. That's this thing, and now we can maybe consider this thing here, all of this mess. And what I said was, okay, look at this object here. What happens when r is 1? When r is 1, you get cos of pi over 2, which is 0, so the first term is 0. When r is 2, you get cos of 2 pi over 2, which is cos of pi, which is minus 1, and that's a 2 there, so this becomes minus 2. When r is 3, you get 3 pi over 2, and again that's 0, cos of 3 pi over 2 is 0, you can check these in a calculator. When r is 4, you get 4 pi over 2, which is 2 pi, cos of 2 pi is 1, times by 4 is 4. And what we realize is that all of the odd inputs become 0, because cos of odd pi over 2 is 0. So that's fine, that all goes away. And the even inputs become swap from negatives to positives with just the r in front. So when you have 6, that's going to be a minus 6 here, because we didn't go back to the negative case. When r is 8, we're going to be positive 8, and so on all the way up to 28. So I can break down this sum into 103 times this thing here. 28 is notice how the multiples of 4 are the positive ones. 28 is a multiple of 4, so that's going to be a positive one. And there's lots of ways of thinking about this, including you could just type this into a calculator. It's not that long to do. Or you can think, well, these two things make a 2, these two things make a 2, the next two things make a 2. How many pairs are there? Well, 28 going up in 2s makes 14 numbers, so there are 7 pairs. 7 pairs of 2 makes 14. Type this into a calculator, obviously you get this. And now we're told apparently that all of this is equal to 3n cubed, and we're trying to find values for which that works. Let's just times everything by 2 to clear that out. Expand this bracket out, tidy this up, and put that in a calculator, and we'll get this. And so the answer for n must be, for positive integers n, must be 29. Good. Question number 7 then. Really interesting complex numbers question. I really liked this one. The first thing I did, so we've got one root, I think, of 3. So when we're drawing an diagram, we can put that root down. Now, the other roots make a triangle. The other two roots must be complex conjugates, right? So if you, say, just put one up here and call it a plus bi, the other one must be on the same kind of vertical line and be a minus bi. And this makes a triangle for me, right? And this distance here is 2b, because it's b plus another b. And this distance here, I was a bit careful with this. There's better ways to draw this, but I said it was this. Because according to my drawing, a is negative. Because, of course, a represents this bit. And so, like, if a was negative 3, for instance, this distance would be 6 from here to here. And that only works if I say it's negative a plus 3. Negative 3 is 3 plus 3 is 6. So that's why I wrote it like this. Of course, if you just drew these things over here, that it would be much simpler to think through. But anyway, I've got this, so therefore my area of this triangle formed by the roots is a half times 2b times 3 minus a, and I'm told that's 35. The half and the 2 cancel to get this, and that's an equation in a and b, whereby a and b are what I've called the complex numbers that I'm looking for here, or the coefficients, or the real and imaginary bits of the complex numbers that I'm looking for, I guess. Okay, what else can I do? Well, I noticed they've actually given me this coefficient of 1. That's quite a hard spot to see, because if it was a 2, I think people would notice it more, but because it's a missing one, I think it's harder to spot. But anyway, this is the sum of the roots, right? So z1 plus z2 plus z3 equals negative 1 over 1, which is just negative 1. Negative, of course, because these are individual roots. But of course, z1 is 3, and I've already said that z2 and z3 I've written like this. So when I add them together, the bi's will cancel, and I'll just get 2a equals minus 4. That should be a minus 1. Apologies, I typed that bit too early. So that's a minus 1. Take away 3 gives me a minus 4. Apologies for that. Anyway, then divide by 2, we get a as minus 2, and we can shove that result into there, and we can get the b as, I believe, 7. And so our two complex numbers are 2 plus 7i, sorry, minus 2 plus 7i, and minus 2 minus 7i. Maybe just look at the picture and verify that that works. The distance here would be 14, the distance here would be 5. 14 times 5, I believe, is 70, divided by 2 is 35, so I'm happy with these. I'm going to go with these. Hence, find the values of p and q. Well, q is, thinking about roots of things again, q is what happens when you multiply all 3 roots together. Well, when you multiply all 3 roots, you get minus q over 1. But that's just minus q, and then move the minus to the other side, and I've said this. So, of course, I just multiply these 3 roots together. These two make 4, cross terms cancel, plus 49 is 53 times those for this. So that's q. And then you could think about double roots to find p, but it's actually easier at this point to consider the function to be this now that we found q, and just shove in 3 into the thing, because you know that's a root, so that should equal 0 when you do that. So that all equals 0. Obviously solve for p, and we get p is 41, and that's our entire question. Really nice question. A really great way of asking about complex numbers. I thought that was really great. I can't be saying the same thing for question 8, which is just 2 proof by inductions. Okay, let's do this. When n is 1, you get just this to the power 1, which is itself, which I guess you could write like this. Just verify that it all works. It does. So true for n is 1. You assume that the thing is true for n equals k when k is an integer. So you assume that this to the power k is equal to this, and that's our assumption step. And then we just investigate n equals k plus 1. So we put k plus 1 into here. But of course we can write that as this thing to the k times this thing to the 1, because they would add together to make k plus 1. This thing to the k is the assumption step, so we can shove that in. And then we can start multiplying out. So we can say this times this plus this times this is our top left term. which is this, and then this times this, plus this times this, which is actually going to give you a positive there, is our next term, and so on, and then simplify all this up and you get this, and then just pray and hope that if you write this in terms of k plus 1s, you can make it look exactly like it should do at the start here. So this, I think, gets to 4k plus 4 plus 1, which is 4k plus 5, so that's perfect, and that's in this form with a k plus 1 there, which is good. This, for instance, is clearly 2 into k plus 1, and the others two work. This is the hardest one to spot, but you don't even have to spot it because you just know that you're looking for 1 minus 4 brackets k plus 1, and you just hope that it turns into this, which it does, which is good. So anyway, that's good. So it works for k plus 1. So if it's ever true for n equals k, it's true for n equals k plus 1, and we already have a case where it's true. It was true for when n was 1, so it's therefore true for all positive integers k. Good, and then we do exactly the same thing with the other type of induction that they like giving, which is indices. So we try n equals 1, we see that it works very easily. You just get 21, which is definitely divisible by 21. You assume that it's true for n equals k, where k is an integer. So you assume this is divisible by 21 for any integer k, and then you investigate what happens for k plus 1. So you put k plus 1 into here, so k plus 1 there, and then k plus 1 in there. You expand that out, you get this, and now you're trying to force the assumption step into this here. So this bit is wrong, so let's just reduce this by 1 in order to times it by 4 to the power 1, like this, because 1 plus this is that. And then likewise here, times it by 5 to the 2, and reduce this down by 2, because that's from the assumption step. Of course, this is 4 lots of this plus 25 lots of this. Break this 25 into 4 lots of this plus 4 lots of that plus 21 lots of that. Of course, factorize out the 4. This is divisible by 21 by the assumption step. This is divisible by 21 because it has a 21 in it, and therefore the whole thing is divisible by 21. And therefore, if f of n is divisible by 21 for any for some integer n, then it's true for some integer n plus 1 or k plus 1 or whatever, and we've already got a case. I've said this all before, haven't I? Because we've done 2 of these in a row. I don't know why they did that, but they did. They just had 6 marks to make up, I guess, to make it get to 80. This is a very long question, number 9, but let's just have a look at it then. So we've got this bottle, which is modeled by 3 sections. You've got a circular section here, a curvy section here, which he's using this curve for, and then another circular section up here. You fill it with water. We're going to find out how much it fills up in. First, we need to find A and B. Now, we can just shove in some numbers here. So, for example, when x is 4, you know that y is 14, so we can just put those values in here. You get this. When x is 1, you know y is 14 plus 4, which is 18. And we get this. We do this, take away this. This is really horrific because the numbers end up being not nice. So you check over your work 100 times to make sure it is right, and it is, but it's just not nice of them to give you numbers like that. Anyway, so that's A and B, so that's 2 marks. Now we need to find the volume that the entire bottle can contain. So, I mean, you could do 3 volumes of revolution, right? But you're told that this is a circular cross-section below CF and between BG and AH. So you can actually just say these are cylinders, right? They're cylinders, radius 4, height 14. The volume of a cylinder is pi r squared h. So you can just do pi times 4 squared times 14 to find the volume of this cylinder, which is that. And you can do pi times 1 squared, because that's just distance 1 across, times 10, which is of course just 10 pi. So that's this section and this section, and all we need is this section in here, which I do need to do a volume of revolution for here. We're going around this way, 2 pi radians, which means it's going to be the integral between 14 and 18, as we saw before, of x squared dy, because we're going around this way. So let's just very quickly rearrange this for x squared, times everything by 15, move the 4x squared over, move the y the other side, and then divide by 4, and I think we end up with this. Shove that into there. I don't need the 4, so I think I just said pi over 4 outside here. Good. Integrate this very easy. Shove the numbers in very easy. You get this. You add those to those 2 values. You get that, and you have your final answer. State a limitation. So, I mean, the glass that the bottle is made of is going to have some thickness, right? Which is going to eat into the volume that you just found. So that's just kind of what I said, I think. And then the label states that you can hold 750. So let's work out what this is. It's that. Now that's not too far away. And actually I ended up looking at this and going, well actually that's probably quite a good model, because you probably don't want to fill a water bottle up right the way to the top anyway. You probably want to leave a gap down here anyway so it doesn't spill. And also, like I said, the glass is probably has some thickness that eats into that model. And so, yeah, I think this is a reasonably good model to work with, and that's what I ended up saying. You did need to, I should have said, yeah, for this mark here, you needed to say something vaguely sensible with words. You also needed to work out this number and show it. So you need to say in questions like this take away, this is that, and then say something. So that was what you needed for that final mark there. Anyway, that's the entire paper. Thank you so much for watching.